That is, uh, today I am discussing about some topics, groups, rings, and fields. It is first part of that fourth module, and it will be essential for discussing that channel encoders in that part, some mathematical part. And here, these groups, rings, and fields, there are some algebraic structures. We have studied some different arithmetic operations and also set different types, different sets. And here this algebraic structure means the combination of the set and the operation that are applied to the elements of the set is called an algebraic structure. That is a set and operations. It can be a set of integers and arithmetic operations such as addition, subtraction, multiplication, etc. It is a combination of these, a set and an arithmetic operation, or any operation, we can say some logical operation, etc. Can be. uh, we can say this algebraic structure means the combination of the set and the operation that are applied to the elements of the set is called an algebraic structure. And three common algebraic structures used in cryptography. Cryptography, we know that some secret coding, that is, we are converting a plain text into some cipher text, a coding, a secret coding is actually that cryptography. Three common algebraic structures which comes as part of this cryptography is group, ring, and field. Okay, that is, algebraic structure is a set of a combination of a set. We have studied what is a set and the operation that are applied to the elements to the set. That is algebraic structure. Three important common algebraic structures are group, ring, and field. We can go into details of all these algebraic structure. Group. A group is a set of elements with a binary operation. For example, it is represented by a dot. That operation can be addition, subtraction, any operation can be. We can define a group is a set of elements with an operation dot that satisfy four properties. Is a set is there and an operation is there. A set and an operation together, it satisfy four properties, is called a group. This set and an operation together, it satisfy four properties. If it satisfy four properties, we will see that which are the properties that that will have to satisfied, then we call it is a group. Okay, and uh, after that it satisfies four properties, it will be a group. We will see that properties. And a commutative group, also called an abelian group, is a group in which the operators satisfy the four properties for group plus an extra property, that commutativity. That is, all the properties, four properties are satisfied, then it is a group. If it satisfies that commutativity property, then we call it as a commutative group, and is also called an abelian group. Okay, uh, the properties of that that must be satisfied by a group. That is, if a set and an operation together satisfy the four properties, then we say it is a group. Okay, first one is closure property. If A and B are the elements of G, then C equal to A dot B. That is, that dot represent that operation. For example, we can take it as addition. Then A dot B, C equal to A dot B is also an element of G. This means that the result of applying the operation on any two elements in the set is another element in the set. You can say set of integers, and operation addition. Then uh, sum of two, the addition of two integers give another integer, and that sum, that result of that addition is also a member of that set. Then we can say that set of integers with addition operation, it satisfies that closure property. Okay, if a and b are the we can define that closure property of as if a and b are the elements of G, then C equal to A dot B is also an element of G. This means that the result of applying the operation of on any two elements in the set is another element in the set. Okay, that is the first property which is to be satisfied by a set, and that operation to be that set and the operation is a group. Okay, then second one is associativity. If A, B and C are the elements of G, then A dot B in a dot C equal to A dot B dot C. That is, you can take that operation as addition. Then A plus B plus C equal to A plus B plus C. It does not matter in which order we apply the operation on more than two elements. That is that meaning of that associativity. If it satisfies the that closure property, that is first property, then associativity, second property, then actually that third property is the existence of identity. For all A in G, A is an element of G, there exists an element E called identity element, such that E dot A plus equal to A dot E equal to A. If it satisfies, we can say the existence of an identity. There must be an identity element which satisfy. If E is the an element and A is an element of that set, then that identity element E dot A, here that dot represent that operation. For example, addition, you can say 0, we can take that E, then A plus E is equal to 0 plus an element gives the same element, existence of that identity. Then the next one is the existence of inverse. For each element in G, there exists an element in element A dash, take it as A dash, called the inverse of A, such that A dot A inverse equal to A inverse dot A equal to E. Okay, there must exist an inverse element. If it has a set of elements and the operation, any operation satisfy these four properties, that is closure, associativity, existence of identity, existence of inverse, then we say it is a group. Okay, that's the group. Then that commutativity, for all A and B in G, we have A dot B equal to B dot A. This property needs to be satisfied only for a commutative group, that is that an abelian group. That is that fifth property. For property plus that commutative property, then we say that group is a commutative group or abelian group. That is about the group. It is one of the algebraic structure which is used in uh, cryptography. That is that coding, that is secret coding. That is that exactly we say about that cryptography. Algebraic structure means a set of elements and operation together, and here this group satisfy these four properties, then we say it is a group. And that fifth property, commutativity, then we say it is a commutative group, and or we can say it is an abelian group. Then some more definition of different types of group. A finite group, a group is called a finite group if the set has a finite number of elements, otherwise it is an infinite group. Okay, a finite group, finite number of elements in the group, then we say it is a finite group. Then order of a group, the order of a group is the number of elements in the group, order of a group. Okay, that's about that uh, group. I think you are following. Please type your message yes or no. We have discussed about that first algebraic structure, uh, which is a group. Algebraic structure simply means a set of elements and an operation. Together we say an algebraic structure. First algebraic structure which is used in cryptography is that group. And group, that is a set of elements with together with an operation. We say it is a group if it satisfies that four properties, that is that closure property, associative property, and the and identity element and existence of that inverse element. Then we say an group. If it satisfies that commutative property, then we say commutative group, and it is also known as an abelian group. All of you please say yes or no. Are you following? Please type your message. No response. Please someone says or no.
സാ കേൾക്കുന്നുണ്ട്.
Okay, okay. Okay, we will see some examples later. Anyway, that is the definition of that group. Then we can move to the another other algebraic structure. Second algebraic structure, the ring. A ring is denoted as initially that group is represented by the letter G. Then the ring here a operation. Here first a set, a set, a group of elements, a set of elements, a set. You know what is the definition of that set? And two operation. Normally it is represented by this dot and a square representation. That is, it can be addition, multiplication, like that. A two operation, a ring denoted by like this set and two operation is an algebraic structure with two operations. The first operation must satisfy all five properties required by an abelian group. That is, that closure, associativity, existence of identity, existence of inverse, and commutativity. All properties must be satisfied. This the first operation. There are two operations in this ring, and the first operation must satisfy all five properties required by an abelian group. Then the second operation must satisfy only the first two. The second operator, there are two operations in this ring, a set and two operations. And then the first operation must satisfy all the five properties which is to be satisfied by a commutative, a group, or an abelian group. The second operation must satisfy only the first two. Then in addition, the second operation must be distributed over the first. And the distributivity means that for A, B, and C elements of R, then we have A, the first operation, then B dot C. Sorry, here it is that first square that represent the second operation. then B dot C equal to A, the first second operation, C first operation, B first second operation in C. It is, if it is the second operation is multiplication and first operation is addition, then we can say A into B plus C equal to A into C plus B into C, like that. This, there are two operations, then here it is, it must be distributed. Distributivity property must be satisfied, the second operation. Okay, it is, first there are a set and two operations, then if it satisfies certain criteria, then we can say it as a ring. The criteria, that properties are: the first operation must satisfy all the properties required by an abelian group, the second operation must satisfy only the first two, then also the second operation must satisfy that distributivity. This we can represent like this. If there are if the A, B and C are the elements of R, then we can represent that it must be set that the set and that operation must satisfy these, then we can say it is a ring. Then a commutative ring is a ring in which, okay, there is some repetition. A commutative ring is a ring in which the commutative property is also satisfied for the second operation. Okay, the commutative ring, it is an extra feature. A ring is said to be commutative if the commutative property is also satisfied for the second operation. Then you can say a ring involves two operations. However, the second operation can fail to satisfy the third and fourth properties. In other words, the first operation is actually a pair of operations such as addition and subtraction, and the second operation is a single operation such as multiplication, but not division. Here it is not possible that division operation. Okay, then that's about that ring, that is satisfying some more features, then we can say it is uh, a ring. That is a ring, all the ring will be a group, algebraic structures, group, ring. Then it is a ring satisfy must have all the features, all the properties of that group. Then the third algebraic structure is the field. Actually we are making use of these different types of field in this cryptography. In our if we go to that channel encoders, we will make use of this algebraic structure field, a certain type of that algebraic a certain type of field, that is that our set is that binary elements, that is 0 and 1, and we are using that uh, XOR addition, that is XOR operation, like that. Okay, then we can see a field is denoted by F, capital F, and a set and two operation is a commutative ring in which the second operation, that is it is a commutative ring, therefore it will be satisfying all the properties of that ring, commutative ring. For we can say that field will be a group and also a field, a ring. It is a commutative ring in which the second operation satisfies all the five properties defined for the first operation, except that identity of the first operation has no inverse. This, the second operation, there are two operations here also. For example, addition, multiplication. You can have that addition and multiplication, the two operation, and a set. Then is a commutative ring in which the second operation satisfies all the five properties defined for the first operation, except that the identity of the first operation has no inverse. And a field is a structure that support two pairs of operation that we have used in mathematics: addition, subtraction, and multiplication, division. Here that division operation and also possible, that is except that division by zero is not there. No, otherwise, that is, it can be an addition, multiplication, subtraction and multiplication, addition and a division, subtraction and division, like that. These two pairs of operation: addition or subtraction, multiplication or division, like that, in this field. That is it's about that definition of that field. That is, it must satisfy all the properties. Then finite fields. A finite field means a field with a finite number of elements. Otherwise, it is an infinite field. We can have different infinite fields also. And here a finite field, a field with a finite number of elements, are very important algebraic structure in cryptography. Actually, we are making use of this finite field. And a scientist Galois showed that for a field to be finite, it is a field to be finite, the number of elements should be p raised to n, where p is a prime and n is a positive integer. That is, a field to be finite, that is a finite field, then the number of elements should be, that is, in that set there will be a set and two operation, then the number of elements should be p raised to n, where p is a prime and n is a positive integer. Then here the finite fields are usually called the Galois field and denoted as GF, then in bracket p raised to n. That is the normal representation. That is, we are discussing about different algebraic structures. We have seen what is meant by a group, ring, and field. Then a type of field, finite field, that is, in which the number of elements are finite. And uh, a finite field, a field to be finite, then the number of elements should be p raised to n, where p is a prime and n is a positive integer. Then the finite fields are usually called Galois field, Galois field, and is denoted as GF, p raised to n, where here p must be a prime number and n must be a positive integer. Then only a field will be a finite field. Okay, a Galois field GF p raised to n is a finite field with the p raised to n elements. That is, it is the normal representation. For example, GF 3 raised to 2. That 3 is a prime number. Then 2, 3 raised to 2. 2 is a positive integer, like that. GF 5 raised to 3. 5 raised to 3. 5 is a prime number and n is 3. Therefore, it is a positive integer. Therefore, it will be a finite field. It is termed as a Galois field, and it must have it. It contains p raised to n elements. If it is 2 raised to 3, 8 elements will be there in that Galois field, like that. A Galois field, it is denoted as GF p raised to n, and here p is prime number and n is a positive integer, and it contains p raised to n elements. Then we can consider when n equal to 1, then GFP fields, that is GF p raised to 1, that is that positive integer is 1. We have GFP field. This field can be the set p, set of integers 0, 1, etc. up to p minus 1. If it is that is here GFP field n equal to 1. Okay, then if set p is 5, then the elements of that set are 0, 1, 2, 3, 4. Okay, up to p minus 1. There will be p raised to n elements. Therefore, set P, we can say GFP field has the elements of that set will be 0, 1, etc. up to P minus 1 with the two arithmetic operations. For example, addition and multiplication. You can consider a very common field of this category that is that GFP field where that P equal to 1. P equal to 1 and sorry p n equal to 1 and here p equal to 2. Therefore the set is 0 and 1. For that binary digits 0 and 1 are the elements of that set, and two operation we can consider addition and multiplication. Actually it is here, this addition is not our arithmetic addition. We will have to consider that this, we can see that GF2 field, the set has only two elements which are uh, a binary digit 0 and 1, and here the addition operation is actually the XOR operation. Okay, in this case, in this GF2 field, that addition, that is there are two elements, then 0 XOR 1, that is while we are reading it is, we will say like that 0 plus 1, 0, 0 plus 0, 0 plus 1, 1 plus 0, 1 plus 1. That is that 1 plus 1 here, it is equal to 0. It is actually we are doing that XOR operation here. Is strictly speaking that operation is XOR. One operation is XOR. That is, if we take the different elements 0 and 1, then different possibilities are 0 XOR 0, 0, 0, 1, 1, 0, 1, 1 XOR 1, 0, 1, 1 XOR 1, 0, like that. That is here that addition operation actually it is XOR operation, and the multiplication operation is AND operation. That is 0 into 0, 0, 1 into 0, 0, 0 into 1, 0, 1 into 1, 1. Therefore that multiplication, that second operation, two operation, the set is 0, 1. It is GF2 field, Galois field, with p raised to n, that p is 2 and n is 1, then GF2 field, Galois field, and the operations, one is XOR operation and the other is AND operation. That is, we are making use of this particular Galois field, GF2 field, uh, during that different coding, that is convolutional coding, that is then linear block code, etc. That is why we are discussing about this field here. Then addition and subtraction are the same in this case, that is XOR. While we considering this, that subtraction, we will have to face such operation. Then actually that subtraction also meaning XOR here, and multiplication and division are the same, that is AND operation. That is GF2 field, a special type of that field. That is, we have discussed algebraic structures, group, ring, field, then field, infinite, finite field. Then we say it is a Galois field. Then general structure is GF p raised to n, GF p raised to n. Then GFP field with n equal to 1, then GF2 field. That is, elements are, the set is 0 and 1, the operations are XOR and AND. And here we can see that that representation, that is 0 and 1 are the elements, then the operation addition and multiplication we are representing. Actually it is that XOR and AND operation. uh, then the addition table and multiplication table and that inverse elements, etc., are represented here. That's about this. I think the no time. We can stop now. We can discuss about different examples of this in the next class. How many joined? 57. Okay. Uh, that's all for today.